This is lesson 25 of the Quantum Mechanics, a mini lecture series titled Matrix Mechanics. So in the previous video, I talked about Heisenberg and his work on the atom. So Heisenberg actually sent the paper containing his formula, PQ minus QP is equal to H over 2 pi I, where I is an imaginary number, square root of -1. So he took this his paper to a German physicist named Max Born. Okay, and Max Born actually took the idea further, and he realized that Heisenberg's symbolic multiplication here was nothing more than matrix calculus. Okay, and so matrix mechanics was used to put Heisenberg's work into a more refined form. And so Born, alongside his student, Pascal Jordan, they basically put Heisenberg's theory into what's called matrices. And a matrix is just an arrangement of numbers. I'll talk more about matrices in subsequent videos, but it's an arrangement of numbers. And so Born and his student were able to take the frequencies of the optical spectra, so the measured frequencies, and put them into what's called infinite matrices. Infinite set of possible arrangements. Okay, matrices is plural for matrix. So suppose you have some frequency f, give it m sub n, subscripts. M means row number, n means column number. Okay, so we can express m sub n as a matrix. Matrix looks like this: f11, f12, f13, dot dot dot, f21, f31, dot dot dot, f22, f32, dot dot dot, f23, f33, dot dot dot, and so on and so forth. Okay, this is a matrix. It's got like parentheses around it. So this is the first frequency value in row 1, column 1. Let's say this one here, row 2, frequency value of row 2, column 3, and so on and so forth. Okay, so that was able to express it in terms of a matrix. Just makes things look neater, actually, keeping track of all the frequencies. And I'll show you another use of matrices. So matrices are sometimes used to solve equations like this. Let's suppose we've got this. For example, let's say, I'm sure this isn't correct, but anyway, we can express these two equations as follows. Okay, so this corresponds to the x values here. So the x is just 1 in this case. This column corresponds to the y values. So you got 1 here and -1 at the bottom. And this column corresponds to the answers, the values here that we see, 2 and 4. Okay, so they're very useful for solving things like simultaneous equations. It could also represent, so Born could also represent the momentum P in terms of infinite matrix, P11, P12, just as before. Same thing with displacement from equilibrium, Q11, Q12, dot, 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 dot. Okay, just sets of numbers. Okay, reason being is because the oscillators, so the atoms in this case, with momentum P and displacement from equilibrium Q, also vibrate with the frequencies given by these values here. Okay, that's why they're infinite matrices as well. Okay, so now PQ minus QP could be represented by a matrix 2 pi I multiplied by some identity matrix. So this is called the identity matrix, capital I. It's the same thing as multiplying by 1 as an analogy, right? I is just 1, 1, 1. So it's got 1s all along its diagonals, okay? As you can see here. Okay. So it's got 1s all over its diagonals. So I'll talk more about this later on, but this is basically the idea. The I just acts as like a 1. And Heisenberg actually formulated, and I should say Born as well, later on, the first complete version of quantum mechanics. Okay, a complete mathematical framework. This is called matrix mechanics. Reason being, it's got matrices, and mechanics, it corresponds to the motion of an atom. Apologies, a bit of a typo here. I should be down here. And same thing here. Okay, and in the previous video too, there was a bit of a typo. I should be down in the denominator, right there.